Okay, here's the second part of the cosmology section, and it's also about measuring distance. However, this is a complete link between first half and the second. We're starting to look at the light and the analysis of light from distant stars to actually work out what's going on. So, I know that at GCSE you did a little bit on redshift, which is where we're getting from light, and you may have done a little bit on Doppler, and I'm not going to make the sales here, but when we watch the lesson you'll see the idea is to do with that spreading out of ripples of energy. So we're going to look at how light waves spread outwards, and by looking at that we can tell how fast things are moving. So just to give us a quick review to start with, here are sound waves from a buzzer on the front of a train, and what's happening is if the train is stationary and there's no wind, okay, the medium that it's travelling through is not moving, then the ripples spread out evenly in all directions, a bit like my picture tries to show. Okay, so it doesn't matter which way they're going at the same speed in all directions. Now, that will be true if the train is moving as well. Okay, but when the first of these ripples that I've drawn was let out, okay, was emitted by the horn, well, the centre of it is there. So that was the position of the klaxon on the front of the train when the first ripple went out. The second one is about there. The third one is about there. The fourth one is where it's shown there. Okay? So all of these are basically showing that the train has moved further along, and because of that what happens is that the ripples get squashed up in front. Okay, it's not about the air being squashed up, although that does come into it when the train is moving. If you've ever been on the underground you'll know that. But what's happening is the source of the ripples is moving its position, and because of that, as the ripples of energy spread out through the space surrounding the train, what happens is what we detect, okay, with your ear, if you are stood in front of it, you are hearing, there you go, you are hearing a note which, instead of the normal one, whatever this note may be, this frequency may be, you're hearing one where the wavelength has been squashed right up. Okay, so the frequency here is much higher. If you're stood behind the train, or the train has already passed you, then what you hear, if you're listening there, is a much longer wavelength. Okay, it's not being emitted differently, but you're hearing it as it moves away from you, so the wavelength has been stretched as it travels through to you. So what you'll find is that the frequency here is lower. Okay, so the note changes depending if something's moving towards you or something's moving away from you. Now, of course, if this was moving really slowly, the train, then dots would be quite close together, and because of that the ripples would be near enough symmetrical. The faster it's going, the further it's travelled between each ripple being emitted, each wave being emitted, and because of that these will be more and more squashed, more and more stretched. And you get to a point with sound that you actually get to the point where all of the waves actually are concentrated in one area at the front, and all of the ripples are in that one place. And what you'll find is that if something was travelling that fast and went past you, when you were stood here, it would travel along with the object, I should say. So as this moves along, the ripples are there crushed in front, rather like water ripples in front of a boat. But when this bit hits you, there'd be a massive air pressure increase, and so you'd hear a great big boom. This is the sonic boom that we hear when things travel through air. You can get it through liquids as well, but it's a bit more difficult because it has to be much faster, because the speed of sound in air is much faster. Now we're going to be doing the same thing because we can't hear things in space. So we're going to be doing the same thing, but not with sound, but with light. And of course, for that to be stretched enough so that you can measure the difference, see a difference in colour, the speed needs to be approaching the speed of light. So these are talking about things that are moving really, really quickly. But the idea is the same as just Doppler shift that you have with sound. Okay, so let's go back. A little bit of background first. We're going to start off because this is where we're starting to think about cosmology itself. There's a lot of things where we're not sure. There's lots of different versions being agreed. Agreed and disagreed, fought over. There's different theories about how space started, how it formed, how it's changing. From ancient times through to modern times, we've still got a couple of theories, main theories rolling around. I think we know the one that most people favour. But some things we can agree on is this principle that we can see. And this principle is known as the cosmological principle. And it means that basically there are three parts to it. Space obeys the laws of physics. Everywhere you are, must do. You cannot break the laws of physics, as they say. We also say it's homogeneous. What does that mean? Well, you can of course be asked in the exam, but it means that basically it roughly, I should say equals, it's roughly equals, okay? So it's roughly uniform density, throughout space on the large scale. Okay, so the full scale of space. So roughly same density near the edges of space as it is in the centre of space. It's also isotropic, single iso means, so tropism is about that idea of space and direction, so you could probably break that down, and basically this means the same in all directions. Okay, so it effectively means not just the density is about the same, but matter is distributed evenly. Now, if we have stars in all directions, okay, there's a little bit of weird stuff. Start thinking about it the more you think about it. So this is not on the spec, but you will probably, if you involve yourself with this kind of thing, hear about something called Olber's paradox. There are a few paradoxes that exist in the world, okay, things that seem to be contradictory, but this is the famous one about space, and it's basically Olber versus Newton. And basically he said that in any direction, if this is all true, okay, up here, okay, these two are true anyway, in any direction you will see a star. Now, what it means is not you will see a star, they're everywhere. What it means is every single pinprick in the sky will eventually have the line to a star. So if you could see far enough, every single piece of the night sky should be filled with light. Okay? Now if you're thinking, but light spreads out. But what it does mean, let's just put this in first actually, the night sky should be white. Or perhaps yellowy. Brightly lit, basically. But it's not, it's mainly black. So, if you're thinking, well, hang on, the starlight fades out, just think, the further you look, or the further distance that you stretch your eyes to see, what you'd see in your little cone as you were looking outwards or the cone of light coming into your eye rather, but if you're looking outwards, the further distance you look, your sight cone would have more, sorry, excuse me, can't spell would have more stars in. So even though they're fainter, you've got more of them, so you should still end up with the same brightness. Okay. Now it does assume that we've got an infinite universe, an infinite number of spheres, and all this kind of thing. But basically, he took some fairly logical stuff. He did some calculations. He knew that light faded away by 4 pi r squared. In other words, the surface area of the sphere, so inverse square law. But he also knew that the stars will be proportional to, the number of stars will be proportional to 4 pi r squared. So the bigger the surface area of the sphere, the more stars you'd actually have in that, on that sphere. Okay, and so they should end up with a constant brightness. Okay, but the reasons it ended up being disproved is that although the maths work, it assumes, well, it had several assumptions, but one, possibly more, was wrong. So it was based on an infinite, okay, uniform, in other words, equal in all directions, as we mentioned above, static universe. Okay, that would work with the 4 pi r squared and so on and so forth. Okay, we say should see a bright sky. One or possibly more. Okay, all the mathematical proof. Say this is in the 1800s, 1826. I said he was opposite, arguing with Newton, but not directly, who was dead for a good 100 years or so. But arguing with the implications of what Newton's observations were. One or more assumptions was wrong. And this is a nice piece of timing. So maybe space isn't infinite, maybe it's not uniform, maybe it's not static, maybe it's more than one of those that's not true. Now we are still going to assume that it's homogeneous, okay, and we assume that it's fairly uniform in all directions, isotropic. So maybe it's not static and maybe it's not infinite. Okay, and this led, say, in the early 20th century for people to start searching for evidence to try to get an answer to this. And the answer, of course, lay in the stars. So here's our idea. If we have a light bulb is moving very fast, for example, and it's moving with a certain velocity. Okay, so our source, just in case you can't tell what that picture is. And what it is as it travels, it gives out a certain wavelength of light. Okay. Now, what we can see is if we are in front of it, we will see a blue shift. It will look more blue. It will look with a smaller wavelength. So here, this distance between each of these wavefronts, I'm going to call lambda, slightly different shape lambda bar, okay, or lambda dash. So what we find is that distance all depends on the speed of that, and of course that's because it's travelling a certain distance in that same time. So effectively the wavelength, or the length it has travelled, is going to be speed of light over the frequency, not genius, okay, but that will give me wavelength there, okay. So what I have to do is I have to subtract the wavelength, the velocity causing the wavelength change from that frequency. So what we end up with is we end up with a wavelength of appearing to be down to the difference in speed divided by frequency. Okay, now we are just measuring that wavelength, but if we happen to know what the wavelength should be, then we can find the change in wavelength. So we can find that change, and that's going to be equal to lambda minus lambda dash. Okay, we could have it the other way round, it doesn't matter, we're just going to assume that it's going to be a positive number, but the maths would work just as well. This would still be true if you were doing the stretched wavelength over here as well. So if we do that, well, what I've got for normal wavelength is going to be speed of light divided by frequency minus c minus v over f. And of course, what does that do? That gives us c minus c, and you end up with the negative v, so velocity over frequency. Okay, so what we can do is, if we want to compare things, then we can actually use this idea of ratios to calculate stuff. So if I want to find out how much that has changed, well, how much that changes, a bit like uncertainty, depends on the value it was in the first place, and so some wavelengths seem to stretch or squash more than other wavelengths. So what I really need to do is as a fraction. So to basically get a true value, generic value, okay, in other words for all wavelengths or for all frequencies, what we need to do is say is delta lambda compared to lambda. Okay, and that will be, well, v over f divided by lambda, which looks a lot like speed of light. So what that changes is the ratio, okay, this idea of ratio of change compared to its original, ratio of the velocity at which that is moving compared to the speed of the light being emitted from it, or the wave being emitted from it. The same maths also works for sound. We shall see that again with ultrasound. So what that does is basically gives us a nice simple idea in that I can think about how much, by measuring wavelength, and how much that wavelength has changed, or if you want to rearrange this and do this in a different way, you can do it, you can check it. It's also the ratio of how much the frequency changes compared to its original frequency, fairly obviously because they all link together, which basically is velocity over velocity of the wave. Okay, velocity of the source is moving compared to velocity of the wave. So this equation actually features twice in the data book. It comes under astrophysics. It also comes under medical imaging. Great, brilliant. We can find out how fast things are moving through space by looking at how far their wavelength changes. But we need to compare it to the original wavelength. So this is where our last chapter, or last part of the chapter comes in. It's all about the emitted spectra from stars. So we need the astrophysics to give us this wavelength that we should have seen in a lab. So what we're doing is, if we know the characteristic frequencies of certain chemicals, for example hydrogen, and we know that stars are containing and fusing hydrogen all the time, then we'll know and look for that fingerprint, and we can see how much it moves up and down the spectrum. Okay, so if we think about wavelength, this is is that long or is that short? Is that long or is that short? You need to know your way around. Okay, so red is at the long wavelength, and as we go up in frequency, we get short wavelength. Okay, if this is your eye, okay, so this is your eye on Earth, and you're looking at something that's spinning, for example a galaxy, okay, if we look at the arms of a galaxy, so the nub in the middle and the, for example, spiral galaxy, a bit like ours, you can tell how it's spinning by seeing the colour change as it spins around. Okay, obviously you won't sit there and wait for the same star, but there's stars all the way around, so there'll be some approaching you, some going away. So by concentrating on them, you can see which way it moves. If it's moving across your path, it's not getting closer, it's not getting further away. So both of these are actually the true value. Okay, so this is no shift here. Okay, no frequency shift and no shift there. This is moved towards the blue end of the spectrum, so this is known as blue shift. And the one that's moving towards the red end of the spectrum is red shift. Okay, it does not look redder, it does not look bluer. It's the wavelength change and get slightly longer or shorter, okay, depending on which way it's moving. So if they get shorter, it's moving to the blue end. If they get longer, it's moving to the red end. Okay, so it's that subtle difference, because these speeds are not huge. You know, these aren't going to be at the speed of light, so these are going to be small changes. Okay, you won't see different colour stars coming towards us as you will going away from us. Now, this would be looking at nearby galaxies. If we are looking at things that are further away, then we actually need to look at how galaxies move as a whole. So if you can't see the different sizes of the galaxies, you're not going to be able to measure that difference. So therefore you're just looking at the average for the whole galaxy. So if we look at different galaxies, and here's our lab reference, in other words, these are the true values, okay, true wavelength values, excuse me. If we look at these, what Hubble spotted was things that were further away, measured using the parsec system, have been moved much, much further along towards the red end of the spectrum. So redshift is where things were going away from us. So basically it shows that all galaxies are, this is very close, but all galaxies are actually getting further and further away from us, and the further they are away, the faster they are moving, the more this has been redshifted. So we are starting to get a greater crushing and stretching of the wavelength picked up on Earth, not given out by the galaxies, that stays fairly constant, but actually by the time it's reached us, has it been stretched? Well, yes, it has. So he used this idea and he plotted a graph to work out what was going on. And effectively, what he found was, as said here, the galaxies further away had a larger redshift. So he plotted the distance that was measured in megaparsecs. So this is big distances. Okay, these are very small angles. And he found that their velocity of recession, the velocity at which they moved away from us, was very distinct, very straightforward, and the equation is V roughly equals a constant times by the distance from us. Okay, distance is in megaparsecs, velocity is kilometres a second. Obviously things are big and fast out in space. And the Hubble constant, you could probably work out, is kilometres divided by second parsecs, but of course parsecs can then be translated into meters, etc., etc. What you will recognise more obviously, I think, is that if this is distance and this is velocity, what you've got is velocity over distance, which of course relates it to time. So time it takes to get those lights gives us this whole kind of speed thing. And just to make it easy, he said just multiplying constant, which is velocity gradient. Okay, so gradient equals h0. Okay, now at this time, this is the 1920s. Okay, they couldn't measure very big distances. if you look at this scale, this is his plotted data in here, so very small amount. This is only going up to about 2 megaparsecs. We can see now and measure with fair amount of certainty much further, and what we've found is that they've adjusted the value ever so slightly, but it's pretty good measurement. And effectively what they found was it gives a value, let's fit it in here, I think, would basically states that the velocity is directly proportional, so again Hubble's law could be quoted. Effectively, V is proportional to D. Okay, so that's Hubble's law, the proportionality, again, not an equals. And what it leads to is that although it wasn't always accurate, there are a few anomalies and so on. Basically, the whole lot does kind of work out, and H0 is roughly equal to well, the way they do it is 15,000 over 220 if we take our value from our sheet here. Okay, so we can work these things out and so on, put them in, you know, that's a fairly constant thing that you can be asked to do. And so what you'll get is roughly equal to 70 kilometers per second per megaparsec. Just be careful, big M, small pc. Okay. Now, there is debate about this value still. We still can't be determined by this. We think it's changing, maybe it's increasing. Maybe there's inflation going on in the universe, etc., etc. So the rate at which it's expanding is a bit interesting. Now, I should say, I've just remembered, there's a fault. This diagram is not quite right. It's actually plotted incorrectly. So this is 80 on the correct scale. So I couldn't find a graph without stealing it from the exam board. I didn't want to do that because it would make it too obvious what they want you to do. Although I've put the kind of cross there and given you the hint, gradient. So this gives you a more realistic scale. Okay, it's the ones that you see are much bigger, so much flatter than it was originally. So that gives us an idea. Space is expanding, and things that are further away are expanding faster. So that hints that the universe is not steady, or it could be expanding but others are growing in the way, so there's a steady state universe theory and so on. However, more and more evidence came to light, and so now we've got not the Big Bang, because that was just one theory at the time. It's more correctly known as now the hot Big Bang. And that's down to some work by Penzias and Wilson, who ended up measuring the cosmic background radiation, which was microwave, so CMBR as it's shortened as. And because of this, they found that wherever they looked in space, they were getting interference with their microwave detector, microwave radio telescope, effectively is what they're using, and it was steerable. So what they found was it was equivalent to a certain amount of energy, E equals HF. Okay, so give you that link there, E equals HF, and that of course linked to something that was hot enough to give that out, and that had a certain amount of energy, and equals 3/2 kT basically gave something that was around about 2.7 K. So the universe is still around about 2.7 Kelvin, minus 270.3 Kelvin. It's actually 0.45, but 44, sorry. But you know, that kind of thing, and it's in all directions. So because of that, they know that it must have been a lot hotter in the past. That kind of threw out the steady state theory because it couldn't explain it. It does link in with an explosion, because for explosions you need a lot of energy, therefore it's hot, and therefore it would still be slightly warm, and there's our cosmic background radiation, etc., etc. There we go. Now, the interesting bit is if we work this all backwards through time, and again, you don't need to do it here, but the time links backwards in with this. You can get your heads around this because it's velocity and distance, so you know that there's a time in there somewhere. What we can do is basically say that as h0 is approximately equal to v over d, what we end up with is this is basically equal to 1 over t. Now what is that? T is the age of the universe, or more correctly, the age at which they started spreading, assuming they were spreading out at a constant rate. Okay, and that works. It gives us the age in seconds, but crucially when h0 is seconds to the minus 1. Okay, so we've given kilometres per second. We got megaparsecs, but the parsec is of course a distance, so therefore you can put the distance. You end up with those cancelling out. Gives us a completely different number, which is much bigger, of course, and therefore our time, much smaller, and so our time is much bigger. So yeah, you can get from knowing the recession velocity, of which is is measured by the movement of the wavelengths of this known laboratory gas that's been heated and observed, and knowing a little bit about this idea of Doppler, you can get the age of the universe. That's pretty impressive stuff, I think, on the best of times. So, really common kind of question, okay? And I should say it was actually proposed a lot of time before this. There was an article that's on the shelves if you could read the magazines at college. November last year, I think it was. And it was Lemaitre who'd actually proposed that this is around about a slightly different value for what we had out there. But let's go back for a little bit of practice. Okay, he had a slightly different version, but let's have a little bit of practice. We've said h0 is approximately equal 70 kilometers second to the minus 1 over 1 megaparsec. Excuse me, PC, little p and c. That's approximately equal to 70, obviously, 1,000 meters per second divided by, what was it? Well, we worked it out, didn't we? 3.1 times 10 to the 16 meters. And so what you end up with is that effectively equals, let's quick check, I think it's I haven't written this down, it's 2.2-ish, I think 2.3 maybe. Oh, excuse me, it says writing 2. 2.3 times 10 to the minus 12 per second. And so if you put your background into that, you'll find that space is quite old. I'll let you do the last bit of that. Okay, how old is space? And if you memorise it in seconds, you're a bit weird. Most people say 13.7 billion years old. There we go. Okay, so how do we get it all back to that thing?